We'll start with Marco. Marco is an assistant professor here at SDU, and today he will talk about one of his research fields, formal methods, and he will present an introduction to formal methods. Marco, are you ready?
Yeah, can you hear me?
Yes, perfectly well. So the floor is all yours.
Thanks, and I cannot see the chat, so if anything writes, please can you let me know, or if you have a question and ask them at the end. Thanks a lot. Okay, so welcome everyone. Thank you for joining this presentation. As Jacopo already told in his introduction, this is going to be an introduction to formal methods. We're not going to delve too much into that. It's more like the objective of this is more to give an overview of the fields, what this is about, and how can this be integrated into our practices, software development and software maintenance, and especially with how this can help in increasing our level of security and trustworthiness of platforms. So let's jump directly in what are formal methods. What do we mean when we say when we use this terminology? Is a very broad umbrella term. It comprises many techniques, and as with something that is this broad, usually the definition gets a bit fuzzy at the border. There are some techniques, some methodologies that is open to debate whether we want to call them formal methods. In fact, many people started using the terminology semi-formal methods to refer to some of those methodologies that we will discuss. But in general, by formal methods, we mean the use of some mathematically rigorous techniques and theories in the engineering of software and hardware. And especially because we want to be able to reason about properties of these complex systems. And as I said, the level of rigor of this kind of techniques and methodologies and tools can actually vary a lot, and we can organize them across a spectrum, going from less rigorous techniques where we actually use some occasional mathematical notation inside English specification and documentation. And this is often what is referred as semi-formal methods, where also the kind of English vocabulary we can use is strictly codified in order to reduce and avoid ambiguity, but still depends and relies heavily on natural language. It's not something that we can actually we can strictly and unambiguously assign meaning to. When we move across the spectrum, we get to a situation where instead of English specification, we start using more structured languages, graphical languages, for instance, all the suite of UML formalisms, flow graphs, these kind of things. Try to dispense a bit the use of natural language, but not completely, as they are going to be a complementary tool to the usual specification and documentation activities. Moving forward, still on the right of our diagram, we start finding more rigorous techniques that start using fully formal specification languages, or use them in a partial specification, meaning that they are restricted to some critical components of our system. But the key point here is that there is a formal definition, the syntax of how we specify things. There are very specific rules codified that are not open to interpretation. And by meaning that it is not open to interpretation, we can actually give to what is written following these rules a very precise semantics, a very precise meaning, where precision is given in terms of some mathematical objects and mathematical interpretation. And this is the fundamental that allows us to use tools from mathematics to reason about the meaning of this specification of these models of our systems. And I was specifically very vague in using the term mathematical techniques because there are many of them, and there are a variety of them, and they are rooted in the fundamentals of theoretical computer science, control theory, and they range from formal logic, formal languages, and automata theory program semantics, type theory, but there are many, many, many more. And something that we're seeing nowadays is an increasing trend on hybridizing these techniques, combining them with, for instance, techniques from AI, machine learning, in order to try to complement or curb some of the complexity and the cost of these techniques as an attempt to scale them to bigger systems, as we will discuss toward the end of the presentation. So, what are the role of formal methods in software and hardware engineering? In general, in software engineering, hardware engineering, there is always some level of methodology that is followed that organize the development process using several phases in a more simple way, using a waterfall procedure, but there are more advanced methodologies that iterate across them in order to include feedback and include experience and evolve the system. It's not the point of this presentation to go through them, but what's important to know is that there are a lot of these phases that goes from the analysis of the system, the specification, design, the actual development, testing, integration, and eventually toward maintenance. And formal methods can actually be plugged in all these phases in order to provide added value. They can be a foundation for describing complex systems. They allow us to organize complexity. It's something that we see continuously in other disciplines about engineering, about anything in the human endeavor. We want to curb complexity. We want to organize that using especially compositionality. And thanks to this, we can use formal methods as a foundation to support reasoning about these systems. And this is especially useful in the analysis, specification, and designing phases because it allows us to reason about the properties of the system and find errors or shortcomings in our design and choices early in the process. The more upstream we can detect errors, the less costly they're going to be. And this is something that is true for any engineering discipline, not just for software and hardware engineering. But as I said at the beginning, this is a complementary approach to any other methodology. It's not something that is going to supplement testing or going to supplement other practices like code review or integration with the domain expert, this kind of established methodologies. Is yet another tool that we need to integrate into the handling of engineering of complex systems. And as in general, that has been one of the topics of this event, especially when it comes to security, is a constant effort of many things. It comes from policy, it comes from management, it comes from availability of resources, culture, sensitivity, but also technical readiness and technical tools and establishing the right procedure and using the right tools at the right moment. And formal methods are yet another tool that can complement what is already there. It's not going to solve everything on its own, but can add a lot of value to our system. And as I mentioned, I tried often to connect with other disciplines of engineering. Mathematical modeling is something that is well established in other disciplines, especially in mechanical engineering, structural engineering. And the problem there is that as our structure, our endeavor gets bigger and bigger and more expensive, more complex, we need a more advanced tool in order to get some sense of some guarantees about what we are going to design, what we're going to realize before we actually hit the final artifact and potentially the cost of failure there. And a typical example, maybe on the extreme of this scale, is the development of C platforms. There we want to be sure that our platform is going to resist the rough battering of C for 50 years, 70 years. It's not something that we can achieve through just mere testing. We saw something that we can achieve by just experience. Of course, those are going to help in our design and realization of this platform, but they're not going to give us any solid guarantee a priori. There is still room for failure. So what we have been doing for ages is resort to mathematics in order to build confidence, to get guarantees. We build models of this complex system and we study their properties. There are, of course, error bars in this. There are some degrees of confidence, but we use our model to get some approximation of what will be our final artifact, how it will behave in certain situation. Then, using this model and under some assumption and confidence in its scalability, we actually hit testing. And testing, by its definition, is not in the real world condition. It's going to be in a lab setting, in a very controlled setting, scaled down, especially because, as in this case of the platform, we cannot have a lab that is as big as the sea. We cannot have an experiment running for 70 years before we start building our platform, or our bridge, or our house, or any other system. So we need also a level of confidence in order to, and a sophisticated mathematical modeling that allows us to connect the prediction we make on the bigger scale with the scale we actually use for testing. An instance here, there is an entire field about accelerated vibration testing that is entirely devoted in doing accelerated simulation of how some structure behaves under vibration, like because of sea waves, and extrapolating the behavior of the scaled up structure out of it. And in this, we have the entire disciplines. The point is that we want to compute, to calculate things, and we want to mechanize all this through finite element modeling or computational fluid dynamics. And all of this is not just a single operation. It's actually a continual loop, because once we have our model, once we have done our testing, and we actually hit the construction of the final artifact, we want still to monitor its health, to monitor how it will behave in the final environment, and compare it to what are the prediction of our model, and use any deviation to on one hand, refine the model, on the other, refine the prediction, and try to foresee catastrophe before it hits. Because the moment we find some deviation, then we can have some heads up, some early warning, and try to react to this kind of new situation. And actually, the accuracy and the faithfulness of the model is something that must be verifiable, as I said, during the life of the artifact, but also before we hit production, using some lab-controlled testing conditions. And this is something established to the point that is part of many certifications in many fields, not only related to security, but even on common things, and to the point that this is something established. Yet we don't have something like this in software, something that is getting closer, but we're not there yet. We have very strong mathematical models of computational systems. We can use those models that are usually rooted in some logical system to give some unambiguous representation and meaning to what we are describing, and use that to build and reason about our systems. We have tools that can mechanize this reasoning fully or partially. For instance, there are automated theorem provers that will allow us to, or help us improving properties as mathematical theorems about our system. There are model checkers that reduce the verification of some properties to logic, as we will discuss, other static analysis techniques. And all these allow us to build confidence akin to what we did, or what is happening in other engineering fields. But all this automated reasoning, although covers all behaviors, all possible scenarios, it only covers the scenarios that we actually design in the model. If our model does not talk about time or does not talk about memory consumption, then we cannot have any guarantee about that. This is something obvious to say, but sometimes forgotten. And the accuracy of the model can give us different degree of confidence and different properties. There are very accurate models that allow us to support verification of existing systems. So we can have a mathematical proof that tells that our component, our software components, behaves as specified and have very strong guarantees. They came at a cost, but in some situations they're actually required, for instance, in power plant regulation or in the aerospace industry. They also support synthesis, that meaning that from the model we can actually use a machine, another program to derive some part of our final system or the entire system, or at least some scaffolding to help the developers design the system. And this will reduce the possibility of errors, will also help us in keeping in sync the model we are using to reason about our system and the final artifact that represent our system. As I said, in order to have accurate models, we usually end up need to pay a high cost. By high cost, I mean a mix of cost in terms of computation in order to do this verification and synthesis and certification, but also cost in terms of the realization and maintenance of the model. This is why often, in many situations, it is reasonable to use approximate models. As in engineering, we allow for error bars, we allow for some confidence ranges. Formal methods for software engineering also support this kind of approach, and what this kind of models, approximate models, give us some refutation. So usually you can over-approximate the behavior of the system, so that means that maybe the system is doing something less with respect to what your model is saying, and this allows us to say, okay, if the model is not doing anything wrong, since our system is over-approximated, then of course our system is going to behave in a safe way. There are also models that do under-approximation, and this allows us to verify properties like our system will for sure reach some nice state, or will for sure be able to complete some assigned task. It may be able to do something more, but we did some other approximation of what it is the behavior of the model of the system. And this is a trade-off in the design and the application of the formal methods, but still is enough to reach high level of guarantees in our system. Just to visualize a bit what I'm saying here, and also to compare what our formal models give us with respect to more established and widespread techniques like simulation and testing. Simulation and testing usually happen on the real system, maybe under controlled condition, like we are not using the production system, we are using some development environment, or especially in a DevOps setting, they're actually being carried out live on the production system. But what the key point here is that they give us partial coverage over the cloud of all possible behaviors that our system can undergo. We're probing some spots. This helps us build some sense of security, but we don't know what may happen in the spots that we were not able to cover. On the other side, what we have is something that is really close to reality, and is something that can be continuously integrated and refined. On the other side, formal methods work on an abstract system, a formal model, an abstraction of what is the real system. On this abstract model, we can have complete coverage of the model, which means that there is still some discrepancy compared to the real system, in the sense that it approximates reality. So this situation is summarized by a quote from Dijkstra, that it says that testing shows the presence of errors, not their absence. By probing the behavior of the system, we can see that something breaks. But the fact that every time we test something, nothing breaks, doesn't tell us that it will never break. And this activity relies a lot on the quality of the testing. And there are ways to improve this quality and the coverage in particular. There are techniques developed in software engineering in the last 40, 50 years already. like coverage measures that allows us to understand how much our testing is stressing our system, how much of the possible scenarios we are actually covering. There are techniques that allow us to be a bit more targeted in this coverage. For instance, generation of tests guided by abstract data types or some abstract definition in our system that allows us to clump together some classes of behavior and just test some representative in that class instead of having to go through all the possible elements in that class. Meaning that using this kind of techniques, whereby, where is my cursor? We can select some of those dots and in such a way that by see what happens, I don't know, on these dots, we can infer what's happening in a neighborhood of this test. And this is something close to what's happening actually in physical engineering, like in mechanical engineering or electrical engineering. Other recent techniques are based on fuzzing that introduces some perturbation on the input of our system in order to explore a bit what's happening in the neighborhood of the points we're probing. And this is often useful to avoid hitting some local minimum or some local maximum, some nice spot that is actually unstable. The moment we drift a bit with our input from that spot, we reach some unstable behavior, some unwanted situation. But at the end of the day, a good coverage is something we can strive for, but is impossible. And it all comes down with having good skills and having a lot of luck. And here experience plays a big role, but again, we don't get perfection out of it. On the other hand side, formal methods can show the absence of errors, as I said, but up to what the model can manifest. If the model cannot talk about memory consumption, then we will never catch errors or issues related to memory consumption. And here the quality of the answers we get from our selection of formal methods will depend a lot on finding the right level of abstraction, deciding exactly what to leave out of the model and what to put in the model. And there are issues here and limitations because maybe we are overlooking some aspects in our modeling that later in the life of our system will turn out to be critical aspects that we overlooked, and now they're coming back to bite us. On the other hand, we have a continuous trade-off between what is the cost of reasoning about this model, how complex it is, how big it is, because we can make a model as precise as we want to the point that we actually get essentially a copy, an exact representation of our system. So we just re-implemented our system yet again. There is no advantage in that. And then the cost of reasoning on that will be exactly the same of reasoning on the original system. So there is still a level of trade-off. And again, in this case, it boils down to experience, to skills, to having the right skill set, the right mindset, the right set of tools in our belt, and also a bit of luck in finding the right things to include in our models. And here's an example of what I'm saying. In the beginning of the 90s, there was a famous and infamous, I would say, bug for the Intel Pentium processor called as FDIV bug. It was a bug in the floating point unit of the processor. What happened is that the bug could not be fixed by changing the instruction set, by changing the firmware of the processor. Intel had to go and recall all defective processor, losing about $500 million at the time. I have no idea how much it is now, but I assume more than that. This is, of course, a high-profile failure. There are many like this. There are many horror stories you see in talks like this one about rockets exploding because some conversion error, and again, millions getting lost. But there are also issues at a more mundane level, less flashy, let's say. And partially motivated by this experience with the Pentium, Intel started investing a lot in formal methods. They were using them already, but they, after losing $500 million because of a mistake like this, they hit the accelerator on top of that. Now, Intel reached the point where they fully formalized, they fully modeled their chip designs. They also formalized part of the tool chain that they give to developers and to OEMs in order to build on top of the machine, like some compiler parts of compiler layers, and it has been a decades-long effort. Still, we have bugs. It was not long ago that there were news about two very famous bugs for recent Intel architecture called Spectre and Meltdown. And the point of those bugs is that they were using some time-based side channel. And they were exploiting some property about measuring times, how much time the CPU would spend in order to execute some instruction, in order to gain some information about what our processes in the system were doing. And so how was that possible, given that Intel invested so much money in fully formalizing the behavior of its chips? Is this a failure of formal methods? Well, the thing is that the model was correct. The problem is that this time of attack was based on behaviors that were not accounted for in the model. In particular, the model they were using were not accounting for the time behavior. They were not including qualities about flow of time, how much time certain instruction would consume, and they were essentially blind to a whole category of attacks. And this is an example. There are many more in the literature. Yes, so again, to iterate, formal methods are as good as the model, and how good is the level of abstraction we select. And so is it actually worth the effort of using formal models? The traditional answer is that they are worth the money if you're dealing with high integrity systems. It means a safety critical system like the one you find in aerospace, automotive industry, the energy sector, where if something goes wrong, if there is a bug, if there is a security attack, then there is loss of infrastructure, there is loss of lives, and usually a lot of money. Other situations are security critical systems like banking and voting, as we've seen yesterday with Lorena and her wonderful talk about the e-voting system and all the risks and effort that go into designing and implementing an e-voting system. And their stakes are very high, are concerning the security and well-being of an entire nation, is something that for sure falls square under something that is safety critical. And then there are situations where the use of formal methods is actually mandated by standards in industry. And interestingly, this is, at the moment, is more limited to those standards that are close by to industries related to, let's say, more, I would say, classical kinds of engineering, like electrical engineering, telecommunication engineering, or mechanical engineering. And these examples here are about telecommunications, and there was telecommunication and the use of certain verification for the chips used in these communication devices. There are some efforts in order to bring this kind of level of awareness about formal methods and include formal methods in other kind of certifications for software, but right now it's still limited and is still related to high integrity systems. Other type of systems are those where early errors detection saves a lot of money. And the example is hardware or a system where the deployment of software, the update of software is very costly or even impossible. This means a lot of actuators, industry devices, or to some extent I would include even IoT, although this is grossly disregarded right now. And of course, there is the maritime aerospace industry as well. Besides hardware, and Intel is a pretty good example of what can go wrong and what are the implications of this. And finally, something that is getting more and more traction in the last couple of decades is system with an unpredictable environment. This means especially concurrent and distributed system. And now we are in the age of ubiquitous computing, cloud, and here the environment, the kind of interaction are very complex, hard to predict, and that means they are very hard to test, simulate, and verify with traditional techniques. So here is a list of some standard or established settings where we would apply formal methods where they're worth the money. But the cost of formal methods, which is usually the main critique against adoption of formal methods, is going down. And we are seeing an increasing adoption of formal methods thanks to the introduction of lightweight formal methods. Those often boils down to formal specifications, and that are used in the phases of analysis or requirements analysis for specification of our system and the design phase in order to catch errors early on in the phase. They are lightweight in the sense that these kind of formal methods have more room about abstracting parts of the system. They can be restricted to some components of the system, and often they are technology agnostic. They abstract from a certain technology, certain programming languages. Often people use the term they are above code level, meaning that changes in the development technologies will not affect the formal specification. And this also means that it's easy to reuse skills and to repurpose components of the team and share components of the team across your organization. Another trend that is on the rise is the use of partial formalization. And here is critical the use of techniques that support compositionality, because it allows us to build and start specifying smaller parts of our system, and then as we gain confidence, experience, and maybe resources from our organization, we can extend the part of the system that gets formalized. And a good point to start are communication libraries or drivers, or the critical part of our system that involves interaction, and where usually the cost of bugs or the consequences of security flows are the highest. Another trend that is helping a lot in the increasing adoption of formal methods is that there are more and more mature tools. Formal methods are moving out from academia and from safety critical industries like aerospace, and there is a lot of backing behind these tools from industry. Prominent examples are Infer, that is financed by Facebook. There is UPA that is being developed by the UPSLA and Aalborg universities with backing of many industries. Another one is a TLA Plus with the backing of Microsoft, and this is a model checker that is targeting specifically formal specifications, but there are many more. And also integration with what are the tools that are used by developers is improving a lot. And this kind of tools like Infer, TLA are getting closer and closer and closer to developers in order to get the bar and the cost of adoption lower, as lower as possible, to the point that they are being integrated in DevOps pipelines. And here a lot of expertise came from actually the aerospace industry, where every build, every change to the code would actually start a whole chain of tools in order to verify any condition and properties that needed to be satisfied, and then the requirements were really high. But once these techniques were in place, then it became cheaper to spread them, to integrate them with existing pipelines. And finally, what I would say is perhaps related to is fueling all these increased adoption is that there is more attention in education toward formal methods. There are programs at the master level, at the bachelor level in many universities. There are a lot of academies or consultancy programs that actually help in adopting formal methods. That means that once something that once was a topic that usually entailed that people had a PhD, now is something that is being used by people with a bachelor degree or even without a degree at all. And just to give some perspective and some number to all this discussion about the adoption of formal methods, there was a very interesting article, and one of the reasons why it's interesting is that it's really rare to have this kind of articles, because engineer loves to solve problem, but often they don't tell us how they did it, or they're not good at spreading information about it. So it was rare to come by this kind of article from Amazon. And what they do here is they essentially report on their experience in adopting formal methods inside their development of the Amazon Web Service platform. In this case in particular, what they were adopting was formal specifications, so they were not stepping at the level of integrating it with actual code production, but was still one of those lightweight formal methods, and it was based on model checking, which is perhaps one of the most widespread in industry right at the moment. What they did was they started using TLA, this formal specification and model checker suite, in 14 large complex systems. They didn't model the entire system. They started by critical components, but they've seen in each of those 14 projects, formal methods added significant values. They helped finding subtle bugs that would not be found by other means, their words, and also they helped give them a lot of confidence to make more aggressive optimizations without sacrificing correctness. And this is especially significant because here we're talking about infrastructure for the cloud. Bugs there can cost millions because a downtime of even minutes, half an hour can have huge repercussion. And Amazon started with using formal methods with just 7 teams. Now they increased their adoption across the organization, but it was just an experiment to evaluate how easy or hard and fruitful it was to use formal methods, especially because seeing how costly it is something easy to see, but quantifying the benefits is usually harder. And what I've seen is that engineers at all levels of their career and education were able to learn formal methods in about 2 or 3 weeks, get fluent in using these tools. And they reported the time for essentially starting from scratch. They had an internal academy to develop these competencies, but they've seen that in about 2 to 3 weeks, they got people up to speed. And just also to get a perspective of how big, how costly it was to actually write down these specifications. All these specifications that are reported here are under 1,000 lines of code. Compared to the size of the product they are verifying, this is obscene. And the benefit is that, for instance, in some of these instances, they were able, in all instances, they were able to find some bugs. One very strange bug that they found in DynamoDB was something that I would say would have been almost impossible to get in with testing, because it needed 35 steps in order to reproduce. So it would be something that humans would have a hard time finding. And especially in the internal distributed log manager, something that is very critical to performance of their entire infrastructure, they were able to implement very aggressive optimization techniques. And this is something that actually happens quite often. Another high visibility example is an optimization of the implementation of the live log in the kernel of Linux. What happened is that using formal methods, and in that case they were using a theorem prover. They managed to certify, to prove formally that one instruction could be removed from the code that handled the implementation of a spin lock. That's just one instruction, one line over, I think was like a 10-line code. But that gave a 4% increment in the performance of the kernel, of the Linux kernel. Scale that for all the instances of a Linux kernel you have in a data center, and that translates in millions of dollars at the end of the year. Here is yet another instance of the use of formal methods in a real system outside the usual instances. And the reason why I wanted to mention this is that here in particular was the main takeaway of this story was not that they found bugs. Of course they found, but that by using formal methods here, they managed to get a much cleaner architecture of this system. The system in the specific I'm talking about is the design of a real-time operating system. So we're talking in the range of millions of lines, and they've seen a reduction of 10 times in the size of code. This is something that you cannot achieve by just writing better code. This is something that you need to achieve by defining better architecture. And what the author of this project detailed in the book is that they think that the main reason behind this achievement is that by using formal methods and formal specification, they were able to formally reason at a level of abstraction that allowed them to see this kind of complication in the architecture they have. And something that they say in the book would not have been possible with more traditional techniques based on UML diagrams, testing, simulation, and etc. And as a last example, and this is about the skill set and the cost of adoption. As I said, often people think that using formal methods require a lot of formation, very highly specialized profiles that are hard to come by on the job market. However, formal methods are taught in many master and bachelor degrees, and also many academies, and already students at the bachelor level have the right mindset, tool set, and techniques to conduct analysis and employ formal methods at the level that is industry level and with high visibility results. Here are some examples. There are many more. For instance, the study that you can see on the side is a bachelor project from Caterina Urban, and what she found was a security bug in the Facebook Connect, something that now has been phased out by Facebook, but at the time was this button you could find everywhere on the web that allowed you to connect to Facebook and interact with it. And what happened is that because of this bug, any attacker that was able to place some JavaScript code on a web page with a Facebook Connect button could be able to steal your credentials and impersonate you on Facebook. How she did that? She had to reverse engineer the implementation of Facebook Connect, model it using Avispa, that is a language for studying security protocol, and then conducted some analysis using the Avispa tool. And this in under 6 months, and counting the time, factoring in the time that she had to spend to reverse engineer Facebook implementation of Facebook Connect. So I wonder how long it would have taken engineers at Facebook to conduct the same analysis. There have been other examples by bachelor students that analyzed the Telegram protocol and suggested a revision of it. And another high-profile study that was conducted at the CWI in the Netherlands found many bugs in the Java standard library some with very serious implication in parts of the library that were seemingly very innocent, like the sorting algorithms used by the collection part of the library. And these are just many, but there are many more. And again, we're talking about work conducted by bachelor students. So why we don't see more of that, especially in industry? Because there is a lot of resistance, especially from senior developers, and there is a lack of support from management due to various reasons. Many are cultural or lack of awareness of what are the benefits. And something that has been discussed a lot during this event is that it's hard to measure, to quantify these kind of benefits and make them visible to management. And again, these things are something that are reported in many surveys, many studies, and this is perhaps one of the main issues that are limiting the adoption of formal methods, rather than actually finding people with the right skill set on the job market. So just to finalize things and to try to put some of the terms I was using in some boxes, there are different levels of formal methods that usually comes with different levels of guarantees and cost in their adoption. At the level 0, we have formal specification, which is to some extent the easier to integrate in existing development models, and also one of the easiest, the cheapest to integrate in your team. And surprise, surprise, one of the most widespread in the industry. The idea here is that we use mathematical languages, formal languages to describe the system under development. We use our unambiguous syntax in order to get semantics and support recursive automated reasoning. And this is often used in combination with other traditional techniques, for instance, because we need to keep these formal specification in sync with what is the actual development phase of our project, what is the code that is realized. There are techniques that belong to the level 1 of the formal methods that help in keeping these two layers in sync, but there are also semi-formal methods that allow to do this, like structured review or structured documentation of the development process. And there are many, many tools baked by industry. One of the main examples is TLA, but there are many more. And jumping to the first layer here, we're talking about formal verification and formal development. Again, very huge umbrella. There are many techniques here. Those techniques can mainly be organized into static analysis of systems, meaning that we look at the system not in production, but on the artifact, on the code, and all these resources, and analyze that and study it using some tool and techniques. There are other techniques that use the synthesis of programs, of part of programs. So there are tools that will write some of the components of our software for us, starting usually from a formal specification. And something a bit in between are tools that will extract proof of obligations. So those are tools that can look at code and say your code is correct if you can prove these and these and these facts. These and these and these statements. And here the cost of adoption is a bit higher compared to formal specification, but especially in the extraction of proof of obligation, those are really usually unobtrusive methods. There are examples like the checker frameworks that revolve around annotating code, so are very lightweight to integrate, but are traditionally more limited to high integrity system and mission critical components of larger system. And techniques seen here in order to achieve this are mainly abstract interpretation, model checking, or advanced type system like the checker framework or the pluggable type system for compilers that I mentioned before. Finally, the last level is the level of theorem provers. And the point here with theorem provers is what we want to have fully formal machine checked proof of the correctness of our system. Meaning that automatically or semi-automatically assisting a programmer, the machine will go through all the steps of a proof, that states that our system is actually the implementation of our system is behaving as supposed to be. And those are one of the main benefits here is actually the possibility to extract code. Many of the famous tools and theorem provers are Coq, Agda, Isabel, Hall, many SMTs or satisfiability and tools. So just to go a bit into the details of maybe one of the most adopted technique in the industry at the moment is model checking. The idea here is that we are going to use a model checker that is a tool, an algorithm that can verify if a state machine, that is a way to represent our system as an object that can evolve over time, so it's very operational, actually satisfy a temporal formula, a formula specified in some kind of logic, usually temporal logic. And the idea is that we use this state machine to model, to represent our system, and the logic to model the properties of interest. And our system, and the guarantee behind model checking is that our system will enjoy the property of interest if and only if the state machine is actually a model for the temporal formula. So if the algorithm will say, yes, this state machine is a model for this formula, satisfy the formula. State machines can be arbitrarily complicated, can even be infinite. There are techniques to take care of this, and like symbolic model checking that are used in Alloy. There are versions of this that can take into account quantitative aspects like times or approximate the models that use probabilities, stochastic rates, these kind of things. So it's a very sophisticated and refined machinery that can be employed. And again, this is the kind of thing that was used at Amazon in the case study I mentioned at the beginning. And the other one is the formal proofs and theorem provers. The idea here is to develop a complete and convincing arguments for the validity of some property of our system. And here we have tools that help us into doing this. And the main reason is that they eliminate every ambiguity and subjectivity inherent on drawing informal conclusion. And often they support the synthesis or generation of code that by construction will be correct, since it started from a mathematical proof of what we wanted to achieve. So to conclude, and the main takeaways of what is this very quick overview of this very big field of formal methods is that formal methods are not panacea. They cannot solve all our problems, but they can help us a lot. They can help us build confidence in our system, and they need to be used in concert with other techniques. They can detect defects and errors earlier in the life cycle of our software, our system, can be applied at various levels of cost and investment and skill set of our team, and can be integrated in many of the existing projects and process models. So in general, they can help a lot us in improving the quality assurance and the quality of our systems, as long as they are used properly, as all the tools. And again, as I said, the problem is finding the right level of abstraction and including in our model the right properties and the right details. So, and with this, I conclude, and I thank everyone for your time and attention. I cannot see the chat, but if you have any questions, I'll be very happy to answer.
Thanks, Marco. I can read the chat. Thanks for your talk. If you have questions, please write on the chat, and I can read to Marco so he can answer your questions. In the meantime, I can start also asking you a question. During your presentation, you had a point in one of the slides expressing or stating that one of the possible barriers for the adoption of formal methods in the real world is the resistance from senior software developer or software developers. Can you elaborate a bit on that, and why do you think there is such a resistance, and do you have any approaches that allows to introduce more formal methods in the real world?
Okay, so it's not something that I think is something that has emerged in many surveys and studies that were targeting especially junior developers, since those were the ones that were more likely to have a background in their education about formal methods. And those were the main two things that transpired from those studies. So again, there are many situations, as the example from Intel, where there is a more established tradition of using formal methods, where this is not an issue anymore, or Amazon, where in that case, the decision of trying to see what was all the fuss of formal methods, if they could apply them in their code, actually came from management. But those are often unusual situations. And what I was referring about this resistance from senior developers or management is often something that has been reported from smaller companies, smaller software houses, where the team comprises of people with many different backgrounds, level of experience, and in a way you can also connect this with the usual not invented here. We have been doing this for ages with just testing or with coverage and this kind of tools. Why do we need to waste half a month or a month writing down a lot of nice diagrams in your tool to see something that maybe in a week with the right test I can find as well? And I think that I can see to some extent why there is this kind of resistance. And the main reason to try to reduce this are, one, I think it will reduce over time with people that have a background, that have been exposed to formal methods and their benefits in their education. As they will advance into the industry, maybe this will reduce naturally. The other is we need to spread these experience reports, these case studies like the one from Amazon, and in order to expose people about these kind of benefits. And the last one is something that has been discussed plenty during these 2 days, is there is a need to make the benefit more tangible. We need to be able to measure it. And the problem is that often, especially in these small software houses and small teams, you don't measure what is the performance of your software. You only are aware of issues when there is some catastrophe. And at that point, it's too late to go back and think about formal methods. Your software is already there. You need to fix the problem.
Mm-hmm. Thank you. If there are no other further questions, I think I still have one. In your presentation, you mentioned a lot of big companies, Amazon, Microsoft, are formal methods applied also, or can be applied also for small and medium companies, and can make like the software develop in bigger companies if they apply formal methods in a way qualitatively better, or at least more secure than the software that a small and medium company will produce?
Okay. I don't have tough hard numbers on this, unfortunately. One of the reasons is usually the big companies that give report information about this. So it's a bit harder unless you finance a dedicated study that goes through medium and small companies to check what is the level of application of formal methods to get a number on this. So it's really something hard to come by in the literature. Saying this, what transpires is that the cost of adopting formal methods is getting lower and lower. So it's getting easier to see formal methods also in these smaller companies. There are success stories there as well. Usually those are connected to companies that, even if they're small, are, let's say, exposed to this kind of the sector, the industrial sectors that are usually more open to this kind of culture. Those are companies that are dealing in telecommunication or in robotics, and they already are exposed to this to this approach, to this idea of mathematical modeling, having certification, having strong guarantees already in the design phase that go beyond complement testing alone. And there are tools that are quite cheap to integrate. There are something that I would say are sitting at the borderline of formal methods like code smells or some heuristics that are almost drop-in plugins for your DevOps pipeline you can use. There are things that like pluggable type systems that can be integrated in your development process in the matter of a week at most. That allows you to annotate your code, to add more information. But one of the issues there is that then the developer must be more active in using the method, although it's less intrusive. And there you hit the problem of support, management, and resources. Because again, it means that, I don't know, 20% of your cost is going to be redirected toward the use of formal methods in your development process. The question is whether that 20% is worth the kind of issues you can avoid using formal methods.